Okay, good afternoon, everyone. So today I will talk about the work that I've been doing with the atmospheres, but I'm also going to talk a bit about the interiors of planets. So first, let me tell you why I think giant planets are important. So these objects are the first ones to form in a planetary system. They enforce the very first millions of years of the planetary system, and that's why they have very key information about the history of the system itself. So it saves in the interior information about the chemistry and the physics of the nebula where they were born. In the case of our solar system, Jupiter is by far the most influential planet of all. So first is the biggest one, and it also influences the dynamics of the smaller bodies, so it's really a very interesting object to study. And in our solar system, we can go there, we can make measurements. We also have good information, make observations made from here, from the ground. But it's also a very exciting time to study the giant planets in our solar system because there are two missions. One is Juno, that is actually arriving in 2 weeks to Jupiter. So we will have very exciting news from Juno soon. And also the Cassini solstice is an extension of the Cassini mission. That was changed the orbit, and it will also give us very valuable information of the gravitational field of Saturn. So we will have very good information of these giant planets pretty soon. But of course, this very detailed information that we get for the giant planets in our solar system, we can combine it with the huge amount of data that we are getting from exoplanets. So from exoplanets, we don't have such detailed data, but we have much more points. We have masses, we have radius. For some of these planets, we even have some atomic and molecular detections in their atmospheres. So we need to combine all this information and learn from each other. So here what I'm showing is stellar effective temperature and semi-major axis. Here we have all the exoplanets detected so far, and the triangles are the planets in our solar system. So the planets are in different sizes according to their masses and in different colors according to their radii. So we see that we have pretty good information for these planets here, the very hot ones. We have masses, we have radius for those ones. Okay, so what I want to understand is like what is all this information telling us about the interior of the planets and about the history of the planetary system. And that's why I'm studying the atmospheres, because that's the information that we are getting. We are observing the atmospheres of these planets. But I also think it's very important to study the interior of the planets as well, and maybe in the future combine this information. So I will talk a bit about both. First, let me tell you a bit of the work that I've been doing with exoplanet atmospheres. So this plot that I'm showing was made by Sarah Ruckheimer, sitting there. Here I'm showing the stellar fluxes. Stars are very, very important when we are studying exoplanets. We need to take them into account because the flux that is coming from the star, especially for these planets that are so close to the star, the irradiation is very important in the chemistry, in the photochemistry of these atmospheres. So what I did is to took different stellar types from Sarah's fluxes, and you can see that the fluxes are very different, right? Especially in this area that we are very interested in the UV. We see that the planet around an F star will receive a much higher amount of UV flux than a planet around an M star, for example. And I was studying the effect of this in the chemistry of exoplanets. So what I did is to put the same exoplanet around these different stars and see which was the change in the chemistry. So these are some of the results that I'm showing, which I'm showing one different species. Here we have water, CO2, methane, and hydrogen. And the different colors corresponds to different stars. So let's say, for example, for water, here, this orange line is the planet around an F star. And then this one is the planet around a G star, a K, and an M star. So you see that the planet around the F star receives a much higher amount of UV flux than the water dissociates and photolyzes more efficiently. So then we have less abundance of water in this case than in the other ones. And since water changes, the rest of the chemicals change as well, because water really drives the chemistry in the upper parts of the atmospheres of these planets. So it's very interesting and important to consider, to take into account the right star when we are doing this modeling. Of course, this chemistry also reflects in the spectra. So here I'm showing our emission spectra. Here is the planet around the F star, planet around the G star, and K star. And since the planet around the K star had a larger abundance of water because it's less dissociated there, then we had deeper water features in that case than in the other one. So we really need to take this into account. And following a bit on the previous talk, I'm also interested in these planets that are that we can observe in the future with direct imaging. And that was one of the projects of the students, like to study the chemistry and the spectra in these planets. So I wanted to mention it here. But now let me talk a bit about the work that I've been doing with planets' interiors. Also, one thing that I forgot to say is that M stars are very special stars, and I've been studying them specifically, so if you are interested, we can talk about this later. But the thing is that these stars are, we don't know much about the UV flux of M stars. There were only a bunch of them that were observed in the UV, and we really need to know more about those stars because they really change the planets, right? So we really need to understand them better. Anyway, now switching to planet interior. I already told you why I think these planets are important. Specifically, in the case of the interiors of planets, we have more information in the planets in our solar system, so I started studying them. And I'm specifically working with Jupiter. I'm involved in the Juno mission, so yeah, I will talk a bit about this. So the thing is that Jupiter, as I said, is the best example of a giant planet that we have. And even though we can go there, there were many missions that went and gave us good information. And we can make observations from here. There is very basic information about Jupiter that we don't know. Like, for example, we don't know what is it made of. And by that, I mean we don't know the amount of heavy elements that Jupiter has in the interior. And that's very key to understand the formation of Jupiter and the history of our own solar system. We also don't know if Jupiter has a core or not. There are different models giving different answers to us, and I will talk about this more. So these are things that we want to know better, and that's why this mission was built. One of the key points of this mission is to understand these things better. So let me tell you, what do we know about Jupiter? So we know the radius, we know the mass, we know the gravitational moments, which relate us to the distribution of the density in the interior of the planet. We also know, thanks to the Galileo probe, the abundance of some of the species in the atmosphere. And the best, I think that the most important thing is that we have the abundances of the noble gases that we can only get in this way, going there with a probe. And that is very key for understanding the atmosphere of Jupiter. But so with this information, we construct interior models. And this is more or less how the interior of Jupiter looks like with the classical models. So we have a very thin atmosphere. Then we have an envelope, mainly made of hydrogen and helium. When we go deeper in the planet, hydrogen doesn't behave as a nice molecular gas anymore. We have another state, which is metallic hydrogen. We also have helium, but there is some evidence, thanks to this information that we got from the Galileo probe, that the abundance of helium is different in this region and in this one. The thing is that the abundance of helium measured in the atmosphere of Jupiter is depleted compared to the protosolar value. And we expected it to have the same value. Helium is a noble gas. And also neon is depleted. So what we think that happens is that helium has a phase separation. So it forms droplets that drain down and also take some of the neon to the interior of the planet. So we will have different abundances in this region and in this other region here. I also put here a core, but as I said before, we don't know yet if Jupiter has a core or not. And these are the results of some of the models regarding the core mass and the total mass of heavy elements. So as you see, we have a big range of possibilities here. And that's why it's very interesting to have better observational constraints to help us to make these smaller, to know better these parameters. So Juno is arriving the 4th of July. So I will probably can give you more information about this after I go there. So maybe I can give one of the seminars about this and tell you more about Juno. That would be very cool. But we will have very good information to make this better. But also, not only from the observational side, we also need to improve our models. And one of the key parameters is the equation of state. So here what I'm showing is the phase diagram of hydrogen. And here we have Jupiter interior. So you see that Jupiter passes through different stages, different phases of hydrogen. And we need to have equations of state that actually show us these changes that in the interior of Jupiter. So there are a couple of equations of state published in the literature in the last years. There are a couple. So we have the one of Salmon and Chabrier that is widely used. But there are also two published in the last years. One is the Militer and Hubbard, published 2013. The other one is the equation of state published by the Rostock team in Germany. And they cover more or less these regions in the phase diagram of hydrogen. And so what I was working with these equations to make them usable for the code, let's say. And it took me a lot, I have to say. Working with equations of state is very tedious, but it's very important as well. But the thing is that using these equations of state, specifically these two, were obtained with the same method, but they give us very different results when we are modeling the interior of Jupiter. So when we use these three different equations of state, this is the internal structure that we get. So here we have temperatures and density. This is the interior of Jupiter. And these are the results when using these three different equations of state. So the results do not seem huge here in this plot. But these differences in the temperature, like with this blue one from the Rostock sim, for example, we are getting a much hotter interior. And this also brings us differences, perfect, when we are modeling like which is the mass of the core and the mass of heavy elements that we are getting. So what we do is to test different values for the mass of the core and for the mass of the heavy elements. And we see which ones are the values that reproduce the observational constraints. And with that, we get an area of solutions, or potential solutions for the core mass and the heavy elements mass. And we get very different results when we are using the different equations of state, as you can see here. So here we have core masses of Jupiter and masses of heavy elements. And these are the range of solutions that we are getting when using the Salmon and Chabrier equation of state, which tell us that Jupiter has a small core, but a huge amount of heavy elements distributed in the rest of the planet. So this means that everything will be better mixed, let's say, the elements. When we took this equation of state, we get a higher core mass, but also we keep having a very high amount of heavy elements in the interior. And when we get this other equation of state, for example, here we get much larger core masses, approximately the same ones as we are getting with these ones. But we get a much smaller amount of heavy elements in the envelope. So the planet will be very not so well mixed, let's say. The elements, the heavy elements, will be concentrated in the interior, in the core of the planet. So they give us very different answers regarding the internal structure of Jupiter. And hopefully, we will reduce this and know better the answer once we have better observational constraints. So one last thing that I want to say is that once we understand the internal structure of the giant planets in our solar system better, then we can go to exoplanets and learn more about them. So the thing, of course, is that for exoplanets, we have much less observational constraints. So the models will be much simpler. At the beginning, the best thing to do is just to consider that we have an homogeneous interior, but we don't know if that's true, so we really need to work this better. But this was the other project of students I had, and that's why I wanted to mention it here, which is to apply these same models that I'm using for Jupiter for exoplanets, and to study the effect of using these different equations of state to see which are the parameters that we are getting for exoplanets. Okay, and then this is my last slide, the summary, the take-home message for the talk. So for the atmospheres, I would say that stellar irradiation is very important. We really need to take this into account in the models that we are doing for the atmospheres to get better interpretations of the data that we are getting. And for the interiors, the equation of state is very crucial, but we are also getting better information from the observations pretty soon, so stay tuned to see what we are getting. And here are the questions that I hope I will solve this summer. So thanks for your attention. Which one? Sorry. Okay. The Rostock, the number 2. I think you have to ask them. I don't know the answer. Yeah.
I don't know the exact details of the difference in respect to the third generation equation of state. I'm an author on the third generation one, but I ran that. I wasn't on the second generation, so I'm not entirely sure the difference. But it does critically depend on the run of
Sure. Yep.
How much does it matter what the carbon
So the thing is that that will matter for the equation of state that you are using for the heavy elements. And for now, we are considering different ones, but we are not we are using water or sand or rocks. We are not using really the exact amount of different heavies. But I think that would be the key thing here for the modeling. But also Juno is going to get better information for water and methane. So that's going to be cool, I think, also. Yeah. Yep. The use for what? I use different ones. So the results I'm using here is for water, is the NIST equation of state for hot water and ICES. But I'm also testing different equations of state for the metal. So I can show you the results if you're interested. Yeah. Yep. The thing is that we don't have lab information yet. So this is all a theory. But the idea would be that the droplets of helium will trap neon. And then when helium rains down, it will take also some neon from the atmosphere. So that's why we are observing a depletion of neon and helium in the atmosphere of Jupiter. Yes. Yeah. So there is, yeah, well, actually there is also the thing that we are using equations of state, one for hydrogen, one for helium, and another one for the heavy elements. But if you have an equation of state that combines all the three together, you'll probably get also different results because you have different things when the molecules interact with each other. Luckily, there was a paper like last week, I think, from Burkhard Militzer showing that actually it's okay using them as separate things for the metals at least. So that's, yeah, that's the thing. Yeah, yeah. Yeah. Oh, the thing is that they are just, so what I'm getting, let me go back. So what I'm getting actually is points. So what I do is to calculate different core masses and different amount of heavy elements, and I see which ones give me a right solution that corresponds to observational constraints. So I get like a cloud of points.
So everything in the cloud.
Yeah. Okay, thank you. And the physics of the nebula where they were born. In the case of our solar system, Jupiter is by far the most influential planet of all. So first is the biggest one, and it also influenced the dynamics of the smaller bodies, so it's really a very interesting object to study. And in our solar system, we can go there, we can make measurements. We also have good information, observations made from here, from the ground. But it's also a very exciting time to study the giant planets in our solar system because there are two missions. Planets are in different sizes according to their masses and in different colors according to their radii. So we see that we have pretty good information for these planets here, the very hot ones. We have masses, we have radius for those ones. Okay, so what I want to understand is like what is all this information telling us about the interior of the planets and about the history of the planetary system. And that's why I'm studying the atmospheres, because that's the information that we are getting. We are observing the atmospheres of these planets. But I also think it's very important. Okay, good afternoon, everyone. So today I will talk about the work that I've been doing with the atmospheres, but I'm also going to talk a bit about the interiors of planets. So first, let me tell you why I think giant planets are important. So these objects are the first ones to form in a planetary system. They enforce the very first millions of years of the planetary system, and that's why they have very key information about the history of the system itself. So it saves in the interior information about the chemistry. One is Juno, that is actually arriving in 2 weeks to Jupiter. So we will have very exciting news from Juno soon. And also the Cassini solstice is an extension of the Cassini mission that was changed the orbit, and it will also give us very valuable information of the gravitational field of Saturn. So we will have very good information of these giant planets pretty soon. But of course, this very detailed information that we get for the giant planets in our solar system, we can combine it with the huge amount of data that we are getting from exoplanets. So from exoplanets, we don't have such detailed data, but we have much more points. We have masses, we have radius. For some of these planets, we even have some atomic and molecular detections in their atmospheres. So we need to combine all this information and learn from each other. So here what I'm showing is stellar effective temperature and semi-major axis. Here we have all the exoplanets detected so far, and the triangles are the planets in our solar system. So the